everybody and welcome to this edition of NPTEL online certification course on microelectronics devices to circuits. We will be now studying an important part of amplifier design, and that is basically understanding the stability, and the stability will be understood from the position of the poles in the S plane, right. So, we will first understand how do you design a S plane, and there how do you, what is a pole, and which we have already done in our earlier section, and then using that pole or the location of that pole, we will try to analyze whether this amplifier is stable or not. What do I mean by stability? Stability primarily means that if you have a sustained oscillation in the output and the peak to peak of the output voltage is constant with respect to time, then we define that to be a sustained oscillation. If the voltage starts to fall with respect to time or rise with respect to time, we define that to be as an unstable element. Especially if the voltage rise with respect to time, you enter into a loop which is never ending, and therefore, the overall gain, for example, if you have positive feedback, right, you will always go on adding voltage to the input, and therefore, the output voltage will be always going on be greater in time domain. So, with this basic background, let me start today's topic and let us see how it works out. So, we will look into what is known as the stability of a feedback system. So, what are the criterias so we will study the criteria for stability in an amplifier design, right. We will also look into the position of stability and pole location. So, how do I relate the fact that where the poles are located and how stability can be ascertained from the position of those poles in the S plane. Now, amplifier will look at single pole response, two pole response or multiple pole response, right. And so, this single pole response, multiple pole and 3 poles, which this single pole primarily means that you have only single pole to the left half plane, 2 poles means there are 2 poles on the left half plane, 3 or more poles is the number of poles are 3 or more on the again in the left half plane. So, I am assuming that all the poles are on the left half plane of the axis. Now, let me explain to you where this concept comes into picture. Generally, see S equals to, right, sigma plus j omega, right. So, this was what a general overall any complex quantity will consist of a real quantity plus imaginary quantity, right. So, whenever you plot this plot where this is the real part on the x axis and this is the j omega part, right, and this is basically the imaginary part and this is the real part here, then we define this to be as a S plane, right. We will see that if I remember in your previous discussion, we were defining the transfer function as, for example, 1 upon S plus 4, right. Now, if you see very carefully at S is equals to minus 4, the value of Hs will actually go to infinity, right, and therefore, I can one of the poles of this session is S equals to minus 4. So, where is minus 4? This is minus 1, minus 2, minus 3 and minus 4. So, if you place it here, I will get a very large output amplitude available to me. Similarly, if let us suppose S square is equals to some say again some value some say 4, then S will be equals to plus minus 2, right. But for plus 2, this is plus 2 here. So, one pole here, one pole on this side, and minus 2 will be one pole on this side. This will be stable, but this will be unstable. So, on the right hand side, this will be unstable on the right hand side, and everything on the left hand side will be stable in nature. We will come to this later on in detail, but just for information sake at this stage, whenever you refer to S plane, it is basically sigma versus j omega. Sigma is the real part of S and j omega is basically the imaginary part, and when you place it in this manner, you get this. If the poles are available onto your j omega axis, this will let you what is known as an oscillatory wave, right. So, I will have an oscillatory wave front here, and sustainable oscillations are available here. So, with this basic knowledge of S plane, let me explain to you the feedback. Now, with respect to feedback systems, we have already seen in our previous discussion that a negative feedback primarily means that the output signal is subtracted from the input signal, right, to produce an error signal. So, not all the output signal is subtracted, a part of the output signal is subtracted from the input signal and an error is taken care of. This error is then added up with the inputs, or this error signal which is available to you is fed into the amplifier. The amplifier again amplifies the signal, and this process is an iterative process through the feedback loop. We have already studied that portion again earlier. Now, as I discussed with you that if you remember how I defined my loop gain was basically equals to A times beta, and this A times beta will be a function of the frequency, right. Assuming initially that they are not, but in reality they might be a function of frequency, right. As we have discussed in our earlier terms, that if you plot A versus gain, a normalized gain in dB versus frequency, or let us say omega, then typical values which you get is something like this. So, this is a mid frequency gain is almost constant from this point to this point, and this is a bandwidth actually, and this is FL and this is your FH, right, this is your FH. So, this part is the part where A is independent of omega, and these are the portions where the gain, this is your gain, gain is a function of your frequency, right. So, with this knowledge I can safely say that for large change in the frequency you might have a change in the value of your amplification factor. At some frequencies the subtraction may actually be addition, that is a negative feedback may actually look as positive feedback, producing an unstable system. I will explain to you how I am talking to it. See, as I discussed with you, if T is a transfer function, will consist of its mod value and its phase, right. And if you have a generic diagram of AF with feedback is equals to A without feedback 1 plus transfer function of with feedback, then as in our case in our previous discussion AF is equals to A upon 1 plus A beta. Then you see that AF with respect to beta comes out to be in S terms comes out to be this, where TS is the loop gain. So, A beta is the loop gain which you see, right. Now, if you carefully again get back to the whole discussion, what we can write down from all this discussion is that A of f j omega will be equals to A of j omega, right, divided by 1 plus A of j omega into beta times j omega, right. So, the loop gain L of omega is equals to A of j omega into beta of j omega, right. Now, this can be also written as, if you want to find out its in a form which is most understandable to most of us, that we find out that its mod value, so the magnitude multiplied by e to the power j phi of omega, right, where phi of omega is the phase which you get. Now let us suppose phi happens to be equals to 180 degree, then my loop gain which is basically my L of omega will actually be negative, and therefore, if it is negative, so this whole quantity becomes negative quantity, and therefore, AF of j omega is greater than A of j omega, right. And that is the problem area, that generally you do have your with feedback gains are increases compared to without feedback. So, x of f in general sense I can write down A of j of omega 180, right, into beta into j of omega into 180 into xi, this will be equals to minus xi. So, xf will be equals to minus xi. So, where A and beta are the basically the feed forward gain and the feedback factor at omega equals to 180 degree. So, what I am trying to tell you is that when the phase angle is equals to 180 degree, your negative feedback actually converts into a positive feedback. So, till 180 you will have a negative feedback and your system will be relatively stable. As you cross 180 degree, your systems becomes unstable. That is what I wanted to prove from the statement as far as this is concerned. So, therefore, as I discussed with you, the stability of a feedback system or a circuit is a function of its loop gain T of j omega, right. Now, if the loop gain unit magnitude is unity, when the phase is equals to 180 degree, then as I discussed with you, T of j omega will be equals to minus 1 and the closed loop gain goes to infinity, right. Why? Because if you remember, it was A upon 1 plus A beta. So, now if your A beta happens to be exactly equals to minus 1, then I get A upon 0, which is basically tending to infinity to a larger extent. The idea is, how do you define therefore oscillation? Oscillation is defined therefore as, even with a small input on the onto the input side of the system or the oscillator, I should be able to get an external oscillations available to me, right, and that is what is an output will exist as 0 input, right. And why this 0 input? 0 input means you do not have any input given as a signal state, but you might have some small noise signal, some thermal signal is available to you, which tries to make it into go into circuit state, right. Now, if you are trying to build therefore a linear amplifier, obviously an oscillator is considered as an unstable circuit. I hope you understand why is it like that. But linear circuit primarily means that with respect to frequency there will be linear rise in gain, let us suppose, but that is not true when you have an oscillator into consideration, right. Your oscillator, sustained oscillation will give you a gain independent of frequency, mid frequency gain, and therefore linear amplifier design with oscillator is a difficult task, almost impossible task. Now, therefore, to sum up all these discussions, these 2 points are very important, that whenever my T of j omega, right, T of j omega is less than 1, so I get a negative quantity, and when the phase is 180 degree, right, then the system is stable, right. So, whenever it is less than 1, A upon 1 plus A beta will be AF will be therefore less than A, and the system will be stable. As when the phase is 180 degree, at that point of time, if your T of j omega, which is transfer function, is greater than or equals to 1, then you get in the denominator you get T of j omega to be negative, and as a result you will get automatically 1 minus small quantity will give you a small output in the denominator, and therefore you will get the system to be unstable in nature, right. So, because it will be rising wave function as such for your case, right. So, this is what you get as far as switching is concerned. Now, let me come to the concepts of poles and zeros. As I discussed with you just in the starting of this module, that for an amplifier to be stable, right, or any system to be stable, its pole should lie on the left half plane of the S plane. So, it is a rule of thumb across the board, and we will see just now a numerical reasoning for that, that if you have S plane, within the S plane you want to generate a stable system, then try to ensure that the poles are actually situated on the left half side of the plane, right. That is pretty important, where your sigma is less than 0. That is very important, where your sigma is less than 0. As I discussed with you earlier also, a pair of complex conjugate pole on the j omega axis will give you sustained oscillations to a larger extent, right. Now poles on the right hand side will always give you an oscillations which are growing with respect to time. So, this will be primarily an unstable design for any oscillator, or for that matter amplifier. The reason being, on the right hand side you will always the output will be always gaining with respect to time, and therefore it will be a never ending process as far as this is concerned. Now, let me come to the explanation here, that if you see this signal S equals to sigma 0 plus minus j of omega n, right, and therefore if this is the value of S which you see, then we can write down voltage. I can just write down for you that let me say it is given as S equals to sigma 0 plus minus j of omega 0, and therefore Vt voltage is given as e to the power sigma 0 t into e to the power plus j omega 0 omega n t, let us suppose, my plus e to the power minus j omega n t. So, this is the sine of omega n t multiplied by e to the power phi t gives you this value. Now, this if you solve it, I get 2 times e times omega sigma naught into cos of omega n times t. This will be your Vt. Now, if the poles are situated to the left half plane, which means the sigma 0 is less than 0, right, then we get a stable system, otherwise we will get a unstable system. Now, if it is less than 0, you will actually see something like this, that the output will be like will go on decreasing as you move with respect to time. So, if you plot a graph here, which is the envelope of the whole design, you will see that the envelope is actually a falling envelope. So, this is your gain, right, in j omega versus omega, right, and this gives you the decay. So, this is basically your envelope of the cell, and as you can see where sigma naught is less than 0. So, you will get e to the power sigma naught coming into picture, which means the sigma naught is less than 0 means sigma naught will be negative, e to the power negative will be actually a falling function, and therefore, you will automatically get a smaller and smaller function in general, right. So, this is the basic concept which you see here, as I discussed with you, is 2 e to the power sigma naught t cos of omega n into t. Now, therefore, if the two therefore, let us suppose you have got two poles and they are on the left half plane and they are complex conjugate. Conjugate means one is a real part and another is one is a real part and another is an imaginary part, and therefore, they are referred to as complex conjugate, right. So, if you have such type of planes, you will automatically get an function which is e to the power sort of j omega n into t, and then there will be a term beta here. If beta is negative, this function will always be a falling function as such, and this is falling down, right, and therefore, the envelope is also falling down, which means that you are restricting the output to a very low peak to peak voltage. Similarly, if in the S plane the design is such that the S falls to the right, for example 1 upon S minus 4, then I get is equals to H s, then I get S equals to plus 4 for the poles. So, which means that it falls on the right hand side of the plane, and therefore, it becomes a sort of a rising function which you see. So, the envelope is a rising envelope and this is the falling envelope of the output side, right. If they are exactly on the plane, as you can see on this graph, then it will always give you sustained oscillations to a larger extent. So, the job of a designer when designing an oscillator primarily is oscillator or an amplifier is that you try to keep your poles exactly on the j omega axis. That makes a sustainable growth in terms of peak to peak voltage. So, that is what is the basic idea is all about, and then we come to the fact that let us suppose that we do have a single pole response, which means that I do have a single design or single pole, and the single pole will have on the left hand side, then we can safely write down A0. So, we can safely write down for a single pole system that I get S A of S equals to A0 upon 1 plus S by omega p, right, single pole. So, we will get only single S function here. So, AF of S with feedback will be A0 upon 1 plus A beta 1 plus A beta. So, you remember it is basically A0 upon 1 plus A beta. So, I am just replacing this A by 1 plus A beta. So, I get A plus 1 by A beta and I get A0 here. So, what I get from here is that my with gain the feedback factor increases. So, I get AS to be equals to A0 divided by 1 plus S by omega p, right, and therefore, I get A with feedback to be equals to A0 divided by 1 plus A0 into beta, right, divided by 1 plus S divided by omega p 1 plus A0 times beta, fine. So, I get therefore, from here if you solve it, I get omega p f with feedback is equals to omega p 1 plus A beta. So, you see your gain your frequency starts to rise with feedback, and that is what you see here. Now, note that while at low frequencies the difference between the two plot is 20 log 1 plus A naught beta, the two curves coincide at high frequencies, right. Physically speaking, at such high frequencies the loop gain is much smaller than unity and the feedback factor is ineffective, right. So, if you remember it was A upon 1 plus A beta, at such high frequencies this value of loop gain, which is A beta, becomes much smaller as compared to 1, and therefore, your AF, which is feedback factor, almost equals to A, and it remains A for quite duration of time, and therefore, the feedback is quite ineffective, right, and that is what we have learned through this discussion. Now, therefore, applying a negative feedback, as I discussed in your previous turn, you are able to increase the bandwidth of the amplifier at the cost of its gain, right. Since the pole of the closed loop amplifier never enters the right half plane of the S plane, you automatically get a dominant you automatically get a much more stable system with you, right. As I discussed with you, the single pole amplifier is stable for any value of beta. Thus, this amplifier is said to be unconditionally stable, right, pretty important statement. that this is unconditionally stable, which means that you do not have to put in extra efforts to get it stable, unconditionally stable. As you can see in my this diagram here, on the left half plane you have got omega pf, right, and this is your omega p, which is basically your left half plane pole, right, and this pole is basically on the left half plane, therefore it is stable, but by some mechanism or other I am able to shift this by doing negative feedback. Actually I am able to shift this pole from this point to this point. So the excess value which you get is basically this much, and that is the reason I add omega p plus omega p into A0 into B. So this extra zone which you get is not coming here, and you get unstable. On the right hand side, if you look very carefully, it is actually a plot of gain versus frequency, and as you can see, as the gain falls down, its 3 dB bandwidth, or it's basically the higher cutoff frequency, which is this one, is actually falling down, right. So gain into bandwidth product again is constant, is the standard rule of thumb which we apply in reality. Now let us look at a 2-pole response or a 2-pole design, and explain to you how a 2-pole design works typically in this scenario. But before we okay, so as I discussed with you that phase should never go beyond 90 degree, right. It should be between 0 and 180, but on the if you want to find out a positive feedback, it should not be above 90 degree, right. Let us look at amplifier with 2-pole response. So 2-pole response primarily means that I have one pole here omega p1 and I have got another pole here omega p2, right, and then I start applying frequency. So I do a characteristics equation, and it is very simple and straightforward. This is the low frequency gain or low frequency parameter which I am fixing up. Now what is happening is that I am varying my omega p1 and omega p2, right, and we check out how things work out. So if you want to solve it and get its pole, the denominator has to be standardized in the form of a square plus 2ab plus c square, and they have done that using this formula, and from here I can get the value of s to be some value. S will have 2 values with plus and minus sign. Similarly q will have, q is basically known as pole or q factor, or the q factor here, right, in q factor it is typically height by the full width half maxima, that is what you define as. So if you have a sharp profile, then you have a high q, because the selectivity is very high. Not only that, its height is also very large. So if this height by this height happens to be a relatively small quantity, but still because of the fact that this gives you an idea about how large is your function which you are dealing with, it is quite an important formula which you see in front of you here. So I get q factor available with me. Now note that omega 0 is the radial distance of the poles from the origin, and q indicates the distance of the poles from the j omega axis. So it is quite interesting that in my previous slide, if you look very carefully, then you will see that for a 2-pole response, as I discussed with you, you have one at omega p1 with a negative sign, you have another with minus omega p2 onto the negative side here, right, on the negative side. Now if so as you increase the value of a beta, or the gain into loop gain goes on increasing, these 2 poles starts to come closer to each other, right. And how it is possible? You see, this is possible because this reason, a naught into beta will go on increasing, and therefore this quantity will go on increasing. As a result, your peaks will be sharp. So corresponding to this you will get one peak here, corresponding to this you will get one peak here, bring it closer and you start getting single peak of a large dimensions within the typical value of sigma, right, and that is an important issue which people are looking into it. Omega 0 is referred to as the pole frequency of the design, right, omega 0 is defined as the pole frequency here, and this pole frequency gives you the value of your this thing. So in a j omega versus sigma plane, if you want to find out, then we define this to be a sigma plane and this to be as a j omega axis. Then if my pole is complex conjugate and lying on the left half plane, we try to first plot them and then check the value of omega naught and omega naught by 2q, which is this distance, right. Now if you bring these closer here, if you bring closer here, then you will see that, let us suppose you want here, then this, and you will have this, right, and as a result what will happen is that you are bringing the poles closer to the j omega axis. So you are allowing it to go for sustained oscillations, right, but that will be only possible provided you are able to enhance the values of your or reduce the values of your q, then only this will be possible. Now, let me come to a two pole system as I discussed with you. Q indicates this is the poles from the j omega axis. The poles on the j omega axis have q equals to infinity, and that makes sense also. So, at if you on the j omega axis you put a pole, right, if you put a pole here on the j omega axis, obviously q has to be infinity, because in this case your s is equals to 0 or sigma equals to 0, right. So, the real function is gone. So, only what you will only have is an oscillatory function because of the complex conjugate pair of output signal. So, what you do is, and I will just give you this thought and we can move forward, that if you have multiple let us suppose I have a multiple system, then a two pole response I can, let me show. As is given as A0 upon 1 plus s by omega p1, right, into 1 plus s upon omega p2, a generalized statement of a two pole network. Then if I assume that this is the time when I will get the overall picture, then I can write down s square plus s into omega p1 plus omega p2 plus 1 plus a0 times beta into omega p1 into omega p2. This must be equals to 0. If it is 0, then you automatically get this function to be high. So, I get s to be equals to plus minus 1 by 2, right, omega p1 plus omega p2, right, this multiplied by obviously plus minus 1 by 2 omega p1 plus omega p2, right, omega p2, and then p1 p2 minus 4 times 1 plus a0 times beta multiplied by omega p1 omega p2. So, the same formula which I have been using it time and again, minus b by a and so on and so forth, and then you get s to be equals to this quantity here, right. And so, as therefore, as a0 into beta goes on increasing, right. So, what happens is that this quantity goes on decreasing, sorry, yes, this quantity goes on increasing, and therefore, this quantity goes on decreasing. When this goes on decreasing, this quantity goes on increasing. So, I will the poles will start moving to the left of the plane, right, or the left of the plane here, right. So, the response of the feedback amplifier shows no peaking at q less than equals to 0.70, right, and that is the reason you will get a stable system at q equals to 7.70. Now, that is also referred to as the maximally flat response, right. If q is greater than that, you might get a peak here, which is not a very good sign. If q is less than this value, then 0.707 or 0.03, my mid frequency gain will be very low, and I will not be able to have a stabilized values of frequency where they will fit with each other in a proper fashion. Now, the boundary case value is at q equals to 0.707, which corresponds to phase margin of 45 degree. So, 45 degree is the phase margin which you see, and then the poles location will be at 45 degree also referred to as a pole position, right. Now, amplifier with 3 poles is that, and I will just explain to you this thing, and then we can move forward. What we say is that the last if there are 3 or more, the last one, which is most away from the origin axis, starts moving to the left away from the pole as the value of the frequency goes on increasing. However, the other 2 poles starts to move closer to each other, right. A time will come when they will actually override with respect to each other and then start moving to the left and to the right, up and down. So, till this much movement you will only have a real frame movement. So, sigma movement is available to you, but beyond a particular point you do have complex conjugate movement of these 2 poles as they move towards the j omega axis. So, that gives you a proper idea about the 3 loop system, or a 3 loop system in a sense is there. It is much more complex conjugate and makes it unstable as such. So, with this let me show to you also, as I discussed with you in the previous this thing, that if you go back, so if you go back to your previous discussion, then you will see that you require such high end maximally flat amplifiers where your gain is not gain is almost independent of frequency. So, let me recapitulate what we studied in this module. For stability, the loop gain has to be less greater than 1 and if it is equal to 1 or the phase margin equals to 180 degree, I enter in the region of instability of amplifier. The amplifier frequency response and the stability is determined by the poles. So, typically if the poles are the left half plane, it is much more stable. Poles in the right half plane of gives rise to growing oscillations, right, and that is quite difficult to achieve. If not difficult, it is not desirable to achieve in common physical systems. For an amplifier or any other system to be stable, its pole should be in the left half plane of the S plane, we have seen that. A pair of complex conjugate poles on the j omega axis gives rise to sinusoidal oscillations in reality, right. So, you will always have sinusoidal oscillation if the two poles are located on the j omega axis in a sense, right, and that gives you an idea about why we are requiring such a concept here. Now, I will just stop this discussion with one small enhancement, and that is known as Nyquist plot, right, and I will just discuss this Nyquist plot maybe in the next turn, giving you an idea what is Nyquist plot, right. We will discuss this Nyquist plot in the next module. Thank you for your patient hearing.